Can you see my screen?
Yeah.
Okay. So like this is the mid-review to like remember what we're trying to do, what our concept is. I'm gonna fast forward the video. So we basically did this video to talk about the elements of water and how it grows cities and how water became part of you know, the everyday life of people and how it became part of their lives, basically. And then we talked about the existing infrastructure, how it's very centralized and how it's invasive, stationary, not adaptive, and like it's based on abundance, basically. And because of scarcity around the world, you know, the water crisis actually created conflicts around the world, blah, blah, blah. And then so we were talking about...
So we're saying that actually the infrastructure cannot adapt to nature changes. So we need an infrastructure that is able to adapt.
So countries used extreme strategies such as like cloud seeding, and also they were thinking of moving an iceberg to the UAE. So we thought...
My God, in the Middle East, people are going nuts, huh?
Yeah. And so other strategies were primitive, or not primitive, but they're smart and primitive strategies where it's decentralized and they used nets basically to absorb water vapor from air, basically. So basically what we want to do is a decentralized water off-grid strategy. We personalize water. And so the concept of controlling clouds, how can we control clouds? Can we siphon them? And so we studied how clouds are formed and how water vapor is captured by the by the dust particles and how they condense on the dust particles and then they form liquid, which is like rain or snow. And then we were looking at light infrastructure so that we are able to take this water, move it. And so we basically, what we want a shared infrastructure on the move. We want a collective one, and that basically agents that basically capture, so slow, retain, deliver, and release. Yeah, and also we want to like to make use of weather data and make our own weather data route to help in like getting water everywhere. I'm sorry.
Mm-hmm.
Okay, so
we looked at
Theo's name wrong.
Really?
he's gonna burn you. It's unbelievable.
I did not see that. Oh my God. Anyway, okay. So we were inspired by you have a detection like
the first.
my eye goes always to the wrong thing. I can't control it. Sometimes actually very annoying. Yeah. It's like if there's something wrong, I'm gonna see it.
So it's OULOS, not OLOUS.
I will fix that. Anyway, yes. So we are inspired by the cloud intelligence, by the phase change from liquid to vapor, and back to liquid. The process of this phase change occurs throughout the journey of in different altitudes. So clouds are formed through an accumulation of these condensation nuclei, which is the water droplets that stick on dust particles. So, and clouds are formed like that. And of course, when they get heavier, release happens either in the form of water droplets or in the form of crystals. So we observe the different behaviors that that emerge on its scale. So we have 3 discrete scales: the small scale, which is the condensation nuclei, the medium scale, which is the cloud, and the large scale, which is the weather patterns. And the next slide. And we use that also in our system. So we have the small scale, which is the agent, which can capture, retain, and release water. And it is able to float also, and should be able to float. And then we have the medium scale, which is the accumulation of agents, and where we see the environmental influence, and the large scale, which is the weather behavior again, where we see we are able to read humidity data, weather data, and the diversified demand. And the next slide. So these are the basic behaviors for our agent. It receives humidity, it captures, and then it should be able to remain afloat. So for that reason, we needed was a very and we seeked for an optimum receiver of water. So we needed maximum surface, which is also a very lightweight. So we wanted a lighter than air strategy here. And the next slide. So we started experimenting with this kind of lighter than air strategies, and then with different qualities of hair.
How can you make something lighter than air?
And this is the question. So we saw, for example, we were inspired by the way that a dandelion, for example, travels. So that something that is so
yeah, but that's not lighter than air. This is airflow.
What you meant?
Like it's the air, the flow of air that moves it around.
But like in general, dandelions, they float in air because they're very light.
They are very light, but eventually they will fall if there's no wind. So they are heavier than air. They're not lighter than air. They are so light, but they can be lifted by the air movement. But that doesn't mean they are lighter than air.
I mean, it makes sense, yes. So, like, basically, wind would be an aid tool to move this agent.
Yeah.
Because, wind will always be there, basically.
I think effectively you cannot do something that's lighter than air. I don't think there's a way.
It's a strong statement, maybe.
Yeah, it is. Well, it is a bit provocative. I think sometimes you can say things like that, but regardless, geometry sometimes and configuration and it could be close to the weight of the air, and that makes something fly. But you need to be a little bit careful about it. In the case
of geometry also, like in that case, helps because of drag to float.
But for instance, a kite is no lighter than air, right?
I think that
it can fly.
actually works also like because of drag, like a kite.
Yeah. Okay, that's interesting.
So we.
Daphne, drink some water.
I'm drinking a lot of water. I'm sorry.
I feel you're struggling. I feel bad, but.
Okay, so we just tested in different amplitudes and winds. Yeah. And we came out with an idea that we could have like two different types of feeders, like the base part that helps floating because we will see next, and the interior part which is protecting somehow the water droplets towards the inside, the interior of the flower. So these vortices are those that create that help it to float.
Mm.
In the next. Okay. How it corresponds to humidity. With some sensors.
Mm. Okay.
Next. So the idea was that we capture water vapor, and after that we found a way to direct water droplets towards the center where there is a retention point. The next line. So these were some experiments that we were doing with how we can direct water and how we can retain water.
Mm-hmm.
And let's skip these three. I think they're old.
So if those things fly, right, and we assume that they fly autonomously because of wind movement and things like that, why are they capturing water? Like, just because they have a bit of extra surface on them?
Yes, we can see also in the next our next steps. But what do you mean? Why they capture water?
I mean, no, not why. It's like, how do they capture water? Because
their surface tension of the fibers of the feathers themselves, they capture the moisture, the water vapor.
No, it's the same strategy with a mesh that we show in the beginning, with a decentralized strategy that can capture water, that can capture water vapor. So as we just have to know where a place with high humidity in the air.
Why do you want it to fly to do that?
So it's easy to move it, it's the idea of.
Yeah, but the reality is that once it captures minimal amount of water, all this thing will destabilize and fall because it will be heavier.
Yeah, that's what we want to discuss with you, which is our next steps, because we also had this issue.
Yeah. But in general, like, water vapor is lighter than air.
And the purpose, I think, for us.
That sounds weird, but
clouds. The clouds themselves, the water vapor on dust particles, and they're able to stay up afloat.
Yeah, that's why clouds float, because water vapor is lighter than air. And actually, it is also a strategy for floating, the same way that hot air is lighter than air, lighter than, yeah.
Yeah, that I understand though. The hot air I understand. The wet, the vapor. Look, I mean, I believe you, but just intuitively, I feel like.
And why clouds float?
Well, don't ask me that. I'm no specialist on clouds. I mean,
because water vapor is lighter than air.
It becomes heavy when it turns into liquid, and this is when rain happens, because as it changes to liquid, it weighs down and liquid drops.
Yeah.
But in general, water vapor is lighter than air. It's like a steam room, for example.
Yeah, because it's warmer as well. It goes up.
Yeah.
But is vapor necessarily warm? Could it be cold? I don't know. Maybe not. Vapor is actually warm, right?
We saw also a Festo example, an example by Festo. That was they used actually a hotter, instead of hotter balloon, a steam balloon, a water vapor balloon.
Look, I'm not challenging what you're saying. I'm just trying to learn. Okay, interesting. So vapor is heavier, is lighter. So if
and the purpose is like we were trying to direct it into places that need water, and we can like kind of simulate the rain, like the clouds can provide the
I'm wondering whether it's actually a mechanism that is a little bit, that justifies a bit more the fact that something flies, because I think flying is something that easily in projects we adopt without actually understanding the consequences, especially in DRL. But I was wondering whether it's something that it can partially fly when it can fly, and then while dropping, it actually collects the water and then bring it down to the ground. So effectively, what is this kind of mesh strategy where it collects water in this cylindrical tower, right? Effectively, what's happening is a lot of vapor is going through this tube, and basically the very fine mesh is collecting the vapor droplets, well, the water droplets, and then leave the air to pass through, and then it collects the water. I guess somehow that's how it works. So it could be, let's say, a similar way of a parachute that is dropping and is capturing a big amount of moisture from the air. And then when it lands, it actually holds this and brings it into the ground. So it's kind of an artificial rain. Now, finding the way to take this device up there and going there autonomously is also something very interesting. So if obviously you're not gonna burn fuel to take something out there to drop it to collect 1 liter of water, but if it's kind of a kite strategy where it actually can go very high without anything than the wind blow, occasionally, it doesn't need to do it every day, and then let it go, it could be a more sustainable, cycle of capturing water. Yeah, but but a kite effectively just goes up because of wind, right? And then you release it. Well, in a way, in a simplistic way.
Yeah.
Anyhow, keep going. I didn't want to interrupt much. I think it's quite interesting. It just needs a bit of rationale in the thinking. And I think there are some separate elements that they kind of don't make much sense. Mm. Well, you can do everything in life. I think you need to find the reason first. Because think about it, you're not going to fly a plane to capture water. Doesn't make sense, right? So yes, you can sense it and you can send a mechanical unit to do something like this, but it doesn't make sense as a total, as an overall story. I think first you need to resolve the story line, the story part of your project, and then try to find the technicalities.
By storyline, as in why do we want to move water?
I mean, for me, the story, I think you described it quite nicely. This kind of, let's call it hair-like structures that they actually float and they go up and they capture the water and then they bring the water somewhere else. I think it's a very nice story. You just need to prove that this thing can actually work like this.
Yeah, exactly. And it is very hard because water vapor is invisible and it's something that we really think how we could test.
Exactly.
Like physically.
Exactly. That's why I think sometimes you're almost touching the invisible part of things. So you may need to adjust a bit your strategy because it may sound good, but maybe it's not. That's all I'm saying.
Yeah, if we think about the reality about the mobility and how it's float, it's quite hard to make it come true.
Okay, but that's the thing. Trying to resolve something you cannot resolve, it doesn't gonna take you anywhere. So maybe this is a starting point of the thinking, but you need to expand the thinking to somewhere that actually you feel comfortable of resolving. So if it's something like a more mechanical system rather than a completely natural one, so be it. But
and it could be hybrid, like it would be in the middle between.
Could be, of course, could be.
Yeah, we thought both cases. We can see that, like in a while.
Like, I don't know, if you think about a kind of a moving cycle, right? So let's say you have a hot air balloon that hits the air because of sun rays, right? And this hot air balloon goes really high because it is actually getting fed by sun, so zero consumption of energy. And up there, it gets released and captures air and comes down. It could be, it's kind of a cycle. So think about zero energy, effectively, or recycling of energy, and probably that's going to give you the more reasonable answer to your question, because what you're trying to do is not really energy hungry. It's effectively you try to capture water. That's what your project is about at that moment.
Yeah, we thought a little bit about this, and we think one possibility about just like the balloon, and we can use helium to like lifting it, and when it's collecting enough water for the weight, and the weight getting heavier, so it's get like naturally drop down. But the problem is in reality the helium like for 1 kilo 1 liter of water is like needs so many.
Also later, because we have the diagram, maybe it's easier.
Okay, that's also interesting.
To explain.
That's also an interesting concept.
Okay.
I mean, look, this kind of thinking, this is what you need. I mean, we haven't gone through all the presentations, so maybe some of the stuff I'm saying they are already there, but yes, it could be something like almost like a ladder that goes up and down, collects water, and is kind of an infinite loop of elevating, getting heavier, going down, and then elevating, and the same.
Okay. Maybe just go quickly with the slides first.
So what are
And
those
this,
cloud formations? Because they look quite interesting.
It's actually controlling with different force, turbulence. But like we were thinking, if our like our architecture could be a smart dust, which can collecting and gathering moisture to become a droplet. So in different cases, like with mobility, it can turns out with different like results like this. Just testing. Okay, maybe next.
Yeah.
And this one, just like you also mentioned a little bit, like if we can put the cluster behavior like a kind of tunnel, and while it's moving, it can collecting the moisture to the mesh system, so it can collect a certain level of water and bring it to a certain place, and some simulation like that. Yeah, and next.
Okay.
Okay, maybe next. Yes, same. It's same. Next. And we're thinking like how we can control like with nodes to control the drop in different ways, and for some simulation and testing about it. Okay, next. The simulation like to get the different float or droplets. And with this also some different turbulence and emitters, or like before it's single emitter, and now it's like multiple emitters and multiple like attraction force, and to create different like separation and gathering. Yeah. Okay.
This is just how we could choreograph the release of water.
Yeah, and like it releases, like we were thinking how it releases the liquid, and then.
Okay, but if you go, can you go to the previous one?
Yeah.
Like as a simulation, I understand it's three different scenarios here, right? But what does it offer, like differently between the three scenarios? What is, except from the sake of experimentation and trying different emitters and amount of particles and all that stuff, what is actually different? And how do you use this difference between the three? I mean, I can see they're different, but effectively all I'm saying is it's kind of what I was saying in the previous team. How do you control it, and why you control it? What are you trying to achieve through that?
I think one possible way is like we want to deliver the water to the places which need lots of water to balance the moisture level and water level. So if we can give them certain like destinations with the control, so it can go to those certain places.
In general, we haven't focused more further on this part, so we can see that in more detail.
I think it's interesting, but you just need to find how to use it.
Yeah.
At the moment, it's just another nice simulation, but doesn't offer anything.
Okay.
Yeah, we're basically divided the whole capture, retain, release, deliver, and release. So for now, we focus on the capture part and the floating part, basically. No,
that's fine. You don't need to. To do everything. I'm just saying this is food for thoughts.
Yeah, definitely. But in this simulation, for example, like we were looking at the emitting part, like how can we control the amount of water released, having one source or three sources, or like this is just basic simulations about release and how it can release in one release or multiple releases, basically.
And I think also there was an idea and the statement that in the part of release, we actually see our architecture being saved. So we could say that either in the form of water that is that drops from air, or in the form of water that gets crystallized while it falls. We could speak about our architecture in that point, because it's not only a way of redistributing water. So it shouldn't be only a water management system. So this part, for example, of crystallization is also important.
And then our third large scale would be the weather scale.
I personally think that it doesn't necessarily need to be an architectural project, what you're doing. And that's not only for your team, could be for all 4 teams. It could be an infrastructure project. It could be a device. It could be something that captures water, which is it's a critical issue. So I wouldn't necessarily say, okay, we see this kind of fancy simulations and we can imagine fancy buildings. I don't see that necessarily. No, I'm just saying architecture. Well, you can call it whatever it is. I'm not saying that you are saying something wrong. All I'm saying is that you could isolate and direct the project towards a more infrastructural approach, which is not a bad thing at all. But then you need to focus more on how the system actually works and that it works and so on and so forth. Let's say the project that collects water, this kind of water tube, is actually a project by itself. If one of the teams were delivering that, that's it. They don't need to deliver anything else, because it has the design aspect, it has the operation aspect, it has the prototype aspect, it has everything. So if you could do something similar that goes to the sky and comes back, it could be enough for a project. Because if we start trying to do too many things, like trying to capture a moment of this water formation and how this becomes architecture and so on and so forth, it widens up so much that actually we are in the risk of not trying to achieve anything, if you know what I mean. So that's something to keep in the back of your minds. What would be the final outcome? What are you trying to achieve with this? But it doesn't necessarily need to be a building. That's all I'm leaving up there. But how do they deliver that? Yeah. What is this water that is running? No. That I understand. I'm saying in your story, right? You're saying those units are flying by themselves, fine. They collect water, right? And then they need to be directed to somewhere, except if it goes randomly. how do they get directed to somewhere? That means they need some kind of navigation system, or
they need to read weather data and follow wind.
okay, sure. So how do they move? Do they have propulsion systems, for instance? Because
I think
otherwise,
for-
yeah, but that means that they will go just vertically down or something similar, but they won't go somewhere else that you want them to go. Okay.
In
No,
our initial story, we wanted to be able to deliver from one place to another, like in the same way, like designing a weather system. We understand that there are some difficulties on that, so we are trying many different things.
Yeah. No, I'm not saying. I think it's good. I think your initial thinking that you will need to deliver to a specific point, it's coherent with your simulations, because the simulations are doing exactly that. You're putting some parameters of humidity and targets and stuff, and then you get, let's say, the optimal path or the way that all these units will go to a destination. It's fine. You just need to think that this system that you're designing needs to also be able to navigate. That's all. So it's another complexity on something that is extremely lightweight.
And it's very complicated. We will see that now. So these are the four main steps that we have: capture, retain, deliver, release. And we focused on the next capture, retain are referred to the agent scale. Deliver is more related to the cloud scale, and release is related to the agent scale. So we have to see what triggers all these steps. And this is the circle of events. It's something that is circular. So in the next. It's interesting that we started making a table of the water that consumption. We made an assumption in the next slide that
it's per day, say, My God, that's per day.
Yeah. That, let's say that if one agent can carry 10 cubic centimeters of water, then we need 1,000 agents to have a shower for one person.
Okay.
Yeah. So, and then we want 120,000 agents for one household per day. So that started creating some headache, because if we want to over design one unit, it seems like almost impossible that we have billions of those agents. And if we have bigger agents, then we have something that doesn't look like a cloud, possibly, and is more like something that hovers over our heads. I don't know. And if we see the next. So the main goals.
How do you specify how much water an agent can capture?
Yes. Okay.
How do you do? What is this calculation?
This was just an assumption.
Okay.
Because normally a cloud can have 6 decimeters. Can have some like a very, very similar, can store a similar amount of water per decimeter. A little bit less. So it's like 6 6.
Yes, but that doesn't mean that you need to make a cloud, because you won't make a
It doesn't
cloud,
mean
right?
it's like a cloud has half density.
But all I'm saying is that if you manage, let's say, to get let's say a handful of what is this water capsules that they collect water, the crystals,
Hydrogels.
hydrogels. If you get a handful of hydrogels and you fill it with water, that's, I don't know, a liter of water or something, right? And you have this device that goes up. I mean, instantly, it's much more than what you're saying here, right? It's exponentially more. So maybe there's other ways that you can make something heavier. Of course, an agent that is heavier as well, but can carry exponentially more water. So you may get, your balance may get a bit better.
The big issue here is that if we go like to the next slide in the floating part, is that next. So we need it to be lighter than air, as we said. Next.
Yeah, but that's not necessarily a parameter. I mean, if you do this kind of helium approach, it doesn't necessarily need to be.
Yes, that's what I want to say now. Next. The problem here is that water vapor is very light. Water is heavy. 1 cubic decimeter of water demands 1 cubic meter of helium, which is again inconceivable as an amount of helium. And again, if we
not that much. Come on, it's not that much.
Instead of helium, we use hot air. Then again, it's like a very, very big amount of hot air has helium has double capacity compared to hot air. So we need 2 cubic meters of hot air in that case. So for only 1 cubic decimeter of water, we need 2 cubic meters of helium. Imagine for 1 shower, we need many thousands of cubic meters, which is not a cloud. It's like immense. And so we had this issue here. So we thought that we have to go back to water vapor, and we have to use water vapor as the lifting force. Okay. And we found also that Festo has used that also as a smart balloon, as a balloon strategy. And that also, like, we just imitate the way that the cloud works, which sounds like silly because we don't know, we don't know how to control that really at this point. It's like that the best thing that we can do is to ameliorate, to create a better behavior in the condensate nuclei, and the way that the smart dust can absorb water vapor. And we can't really control the way it float, but maybe we can discuss that with you, that how this intelligence could be how the condensation nuclei communicate with each other and deliver water finally.
I think the delivering of water is the least of the problem here.
Floating is the problem?
Well, elevating, capturing, and collecting in a way. Like, The delivering, I think, is another aspect, another complexity. But I think the first parts, let's say, of the system also are challenging, and actually quite challenging. Because we are talking about such a small margin of weight, weight to efficiency, water collection efficiency ratio, which is on the other hand, how the cloud has so much water in it? Is it just a volume that is massive?
It has a great volume, actually. What we say here is that we are doing a cloud, actually. A cloud stores water vapor, so why not? What do you mean? How it stores so much water?
No. I'm not trying to find an explanation. I'm saying just how is it possible it can hold actually so much water in it? And then we struggle with the basic calculations of how we can lift water up, well, lift vapor. And then for a shower, you need 120,000 of these units. Like it's just a bit of a philosophical question. Like, how is it possible in the cloud to be a cloud being so efficient with carrying water? It's just doesn't require an answer.
But basically the clouds, the water vapor in the clouds, or like water vapor in general, they're distributed in a way that they're making this, they have this a lot of water vapor content.
Yeah.
And the key is distribution also, like the distance from one water vapor to the other, one particle to the other.
Yeah, and about lifting and balancing and dropping, it's about the density. Like if the density is smaller than air, so it's going to be lifting up. So when cloud is like balanced with air, so it's going to float, and it's heavier, like the density going to be larger in amount, and it's going to drop.
I mean, it's something that happens, so it's something that we can reproduce also, but we can't really test it. It's so invisible. I don't know.
There's this article that says that the cloud weighs as much as 100 elephant, basically.
Yeah. Well, that was my philosophical question. How is it possible something that flies to have so much water content?
Yeah.
That was a bit where I was going. Okay. Well, I don't think we are going to solve it now. I think from the way I see the whole thing going, I think there is some quite interesting stuff, but we need to be careful that we are not getting trapped into that, because it could be a tunnel without end. I think you kind of realize that there is a little bit of complication here. So I think we need to do some steps backwards without losing too much work, but I'm not 100% sure in which direction.
So
Sorry?
Sorry.
No, go.
No, we were just saying, like, one of the scenarios that it makes sense was the drop down scenario where, like, if there is humidity in the air, and there is this cloud called Virga cloud where it doesn't rain. It does have water vapor, but because of the temperature, the water vapor evaporates if they go down, basically. So, like, one of the scenarios we were thinking, what if, like, this Virga cloud, there is humidity there, but it doesn't go down to the ground where it needs water. So the basic scenario of drop down, where when there is that, our agents are basically in that area, if we can pinpoint the humidity area.
For me, the problem is not about the system necessarily, it's about the capacity of the system. Because even if you do this kind of, let's say, technique, moving up and down, or the amount of water you capture is actually nothing. Or you need a really high number of agents, which is, again, excessive. So I think that's where the problem is. If it was a very efficient method, I would say, you know what, let's try to find something. But this is not efficient. That's where I'm.
I mean, people, like the Warka towers, basically, they collect water vapor, and they're efficient in a way that they are multiple towers in a village. Like, this village has one, the other village has one.
Yeah.
So I guess
also they're not flying.
They're not flying, yeah. But the technique itself is like using the textile itself to capture this water. And
yeah, but even if you see volumetrically, this tower is like 10 meters tall and 3 meters wide, and it gets a bowl of water.
Yeah.
So no, it gets how many milliliters per day? We had it somewhere. I think it's 80 liters per day.
Well, it could be a very efficient system. I'm not saying the opposite. I think it could be a very efficient system, but still, volumetrically, compared to how much water it has, you'll see that it's a big device that collects a small amount of water. But of course, it could be efficient compared to your system here.
Sorry, I didn't, I'm not sure I get it.
All I'm saying is that 80 liters is quite a lot of water if it can generate. But even proportionally, this object, which is quite big, compared to the volume of the water that it collects, it's quite many times bigger, right? And percentage-wise, what you're proposing, which is a kind of a much smaller unit, it gets minimal amount of water, but the percentage of the unit itself with the water that it collects could be the same ratio. But these towers are actually quite efficient, it seems, in terms of the number of liters they can collect. But I think we're a bit stuck on it. I don't know how to help you now. Look, let's don't get stressed about that yet. I think we just need to think about how we change a bit trajectory of where you're going. I mean, that's what I would say. I think a solution would be this kind of, let's call it, if you had this tower, right? A similar example of this tower that can move up and down, and this process can make it capture water. Or if you can direct it to go to areas where there's higher humidity and can collect more efficiently more water, this could be a way forward. right? But I don't think trying to make a cloud, like a natural cloud, would be the way that you should be going. Let's put it that way. That's my opinion. If you manage to get something like this tower, but in a flying mode, where you can direct where it goes so it becomes more efficient, and there is a kind of energy-free process of taking up in the air and down while collecting more air, more water than being fixed in a location, I think this could be something.
I'm not sure that we have time to start from the beginning, Apo. We have
No, it's not the beginning.
The beginning, like
we
touched up. Yeah, we touched up in that. Like we have a simulation talking about that.
It's just
Like,
converting the project a bit. I'm not. I mean, 100% agree. You shouldn't trust what you've done. I think it's good stuff. Sometimes research is not a linear path, right? You need to go back and forward again. I think you've done some good stuff. You need to filter what is important and then move on to what can give you a solution. I don't think it's far off from what you have. It just needs to be adapted. Otherwise, I don't know how I can help you. I mean, and it's not about me, it's about you.
Like I jumped to a simulation that we were talking about, like dropping the one straight left, like longitudinally, vertically.
Sorry?
Like we did some simulations speaking on that, dropping it vertically, basically, not horizontal movement, only vertical.
Okay, but let's think about positively, right? These towers that they're so efficient, right? What is their weak point? What can it be done better? How can you increase their efficiency?
The weak point is like they fixed in one place.
Okay, good. So it's not everybody that they take advantage of it, number one. But somebody would say, okay, build another one, is cheap. But what is the other problem that they are fixed?
The amount of water, like the capacity, just like what you said.
No, but is it because sometimes in a specific area where those towers are fixed, they don't get the optimum amount of humidity? They may get drier climate, right? So you can navigate those ones to areas that they are more humid. So if it's a system that actually can have a more nomadic cycle where they go actually where they can collect the best, is actually a good starting point, right? You're trying to find a device that reads humidity, reads the weather data, and goes where it needs to be to collect the most amount of water, right? I think it's already good thinking. Then you need to find the strategy of moving, which flying is actually quite an efficient one, right? You don't need, it can be in the most hardcore environments, it can be up in the mountains or down in the sea. So flying, it's appropriate, which is good. I think it could be a good story.
But what's the difference in that case? I mean, again, the problem is the weight of water, no?
But it's not going to fly with the water. It's going to fall with the water.
Yeah, we agreed that water vapor is less, like it can float.
But the assumption here was the same that when it has water vapor is up, and when water vapor condenses and becomes liquid, it falls. So if we only could control, if only we could control the location of the smart dust that we have, that we make. This would be the intelligence of the system, because we have water vapor that is lighter than air, and when it condenses, when it is on the right altitude, that because of temperature, water vapor becomes liquid, it will fall. So it will deliver water.
Yes, it will. I mean, as a story, it will. The question is, how do you control this location where it's going to drop it? Because if you think about being a mechanical system, no matter how lightweight it is, the vapor will never make it fly, because it will have enough extra weight to not being able to depart ever. Being realistic, right? I mean, we can say anything, that there will be some new extra super duper material that will be zero weight, but it's not. So in the next stage, I mean, even if we assume that all these things that you're saying, it could be correct, I'm not against it. If you have to build it, right, you need to do a prototype that does exactly that. Do you feel confident you would ever be able to do it? Like make something float with vapor?
No, this was
so we are not going to hit the wall now, we're going to hit it in the next day. So, but I'm confident that you can make a structure like this tower fly to some kind of degree. And because it's actually, as a device, is more efficient. I'm not saying you necessarily need to go for that. What I'm saying is just, I'm kind of skeptical to go to this kind of micro, mini, tiny scale where actually we can't do much. That's what I'm afraid of. And we go to the supernatural, which again is quite challenging to control or design.
Another solution could be that we have a tiny amount of helium that helps us, or water, I don't know, and that helps us only to lift the mechanism. But it still works with water vapor and everything.
Okay, that totally agree. Very good idea. But the ratio of the weight of this device, even if it's zero balance, right? The mechanics with the helium, maybe they get equalized, fine. But then you say that the efficiency of the system with the vapor is actually so minimal that you will need millions of these devices, right? So this problem doesn't get resolved. I mean, not that it's getting resolved easily with the other solution with the tower, but I'm saying, because you have that slide with the calculation, which is a bit worrying. You know what I'm saying?
Yeah, I agree. It is worrying. I was also scared when I saw that.
It's like sometimes something don't make sense and you need to find a different way. It's not, the thinking is correct, the research is good, right? All that stuff are good, but what we're trying to do is wrong. I think we need to rethink. And I totally understand the problem of time. I'm not saying you're going to resolve it necessarily, but it's good to think, and it's good to estimate what would be required. And actually, for your presentation, the final one, be ready to acknowledge that fact and show them moving forward. It's not the finish of the project, right? You have quite a lot of months to develop it, but it needs to start getting some clarity on what you're doing. It's good for you, especially, not for anybody else. We don't care about the rest. Look, let's don't get panic about it. Let's keep going. Think of the problems, and let's try to think what is a different solution. I think what you're proposing could be one way for the moment to move things forward. Right? Equalize the weight of the mechanisms with a minimal amount of vertical lift, which could be helium, it could be hot air, it could be energy, right? Propellers, anything. It could be a drone that does the job. And we can do that for now, but then we need to rethink the strategy. Does it make sense as a plan? Kind of.
Yeah, I think.
Yes, let's see that. Maybe it's not that huge. If we think like the cost of creating a dam, for example, maybe the cost of creating 1 million of that kind of agents is not that huge.
The cost may be not huge. I think is the perception of it. Look, again, as I said, let's don't panic. Let's don't change everything now. It's not the time for it.
That's why I mentioned like also this part. But maybe it's, we have to think that when it's such a huge solution, like when we speak for something that is water management, which normally costs so much, maybe, I don't know, maybe we can accept.
Yeah, but the thing is that don't do the calculations for what a water dam collects compared to that, because there will be a lot of zeros to fill the whole screen. You know what I mean? It's like, it depends what we're comparing.
Yeah, but water dam loses also a lot because of the evaporation. I mean, it's totally different way of functioning.
Yeah. Well, as I said earlier, let's keep going as is. Let's try to think about this strategy of equalizing, because you will need to have some kind of navigation, computer vision, weather data analysis or something on your unit to just direct it to the right spot, right? So this, let's say, primitive but still heavy equipment, we need to equalize with some amount of surface area of some lifting agent. Either it's helium, hot air, energy, or whatever it is, right? And then let's take it from there. Is that happy with that? I mean, I don't think we can actually do something else.
Yeah.
Okay. Should we discuss again once you get a little bit more your thoughts around it?
Yeah.
Yeah, we can show you the rest of the things so that you have an overall idea of what. Yeah. Maybe I'll play this simulation. Yuji, you want to talk about it?
Yeah. But in this one, if you have clustered humidity in the air, it wouldn't be normal that the cubes go to that location at least to collect more of the humidity. Yeah. Also, why the agents are going from top to bottom and they don't go from bottom to top? You didn't what? You didn't write that. Okay. Okay. It is like this, but shouldn't be like this. It's all right. I mean, we can always think about this navigation being something that uses the wind flows to do that. So it's not like a navigation as such, but it's like a controlled fall. We don't necessarily need to look at it like, you know, it has a steering wheel and it goes left or right, and then it goes to point B where we told it to go. It could be something that is a little bit more free. Okay. That's it. Okay. God, now my brain is burning.
Well, can you go to next?
Sorry? Yes, we need to. Oh, guys, except if you want to do tomorrow.
Can we do it tomorrow so that Yunpeng can join us as well?
Oh, yeah, that's fine. Should we do tomorrow 6?
Because it's 3 in China, I think.
Yeah, that's fine.
Yeah.
It's all right. Let's do. I'll arrange that for tomorrow with you.
Yeah, whenever.
Yeah, after 6 should be good. I mean, I may manage to get some time earlier, but let me see a little bit.
Am I showing the screen?
You do? I just need to see about tomorrow. Let's say provisionally 6, but I may be.
Okay. So you'll send us an email with like a Zoom.
But we'll meet tomorrow.
Yeah.
But I don't know the timing. Get ready after 4. Get ready that I may send you an email.
Okay.
For earlier, but otherwise it's going to be 6. Okay. Okay. So what is this in the screen? Is it from you, Ula?
Yeah.
Okay.
Yeah.
Like this is the attempts that we had to integrate like data and to import like data from NASA and try to control like our cloud following this data. So topography and humidity. But we're still on the previous one.
It's actually quite interesting stuff here.
I'm just trying the video. So
doesn't play.
Something moves.
Okay. Let me play it here. Basically, you see how it follows the map.
Is it reading the pixels?
Yeah, it's reading the humidity data, so it's going from an initial point of a high humidity to a point that has low humidity, and we want them to be delivered, for example.
Is there a way you can actually control the clouds?
Actually, I'm thinking before we were thinking about the ceiling logic, the ceiling logic. Like when the cluster get together, it's gonna have the force against the wind, so it's the wind push them to a certain direction. So if we can control the cluster behavior, so it can can control the direction.
Yeah. Well, I was asking more about, can you generate a cloud? Is it possible?
There is a way to do that in a jar, like, and close the lid. And
There are like installations, for example, from artists that generate clouds using the water vapor. Yeah, water vapor. Yeah, but like they can mimic a cloud formation ish.
Yeah. Is it like, I guess they emit vapor, and this vapor is altogether is creating a cloud, which then gets dissolved in the atmosphere because it is drier, I guess. Correct?
Yeah.
Yeah, I don't know how the artists create that, because there is also dry ice that resembles to clouds. So
yeah,
maybe they use just dry ice.
Never trust the artist.
I don't know. I mean,
It can always be fake.
Okay. This one, I'm just thinking like about the smart dust and the agents. If we can put the material on it, like before we are looking at hydrogel, but not necessarily like hydrogel, but something can contain water and
You know what I'm
can
thinking? I'm
deliver.
thinking. Sorry to interrupt, Tyler.
Okay.
I'm just thinking whether we actually go too moralistic on that and we try to change the world instead of looking at our asses and say, okay, you get some very nice geometries on the right. What about if we use this system to produce some cool architecture and that's it? You know what I mean? I'm thinking
Yeah,
a
I
bit
get it.
cheeky. I'm thinking a bit cheeky here and say, it's not always trying to change the world. Maybe there's, design with the water in mind and the change of phase of water. It could be a way to turn a project like that into architecture, or a kind of a cloud formation, or the behavior of a cloud and how all these vapor / dust particles, they come together and they get affected by air movement and the climate conditions. So whether actually, partially we simulate that, partially we generate something that is a representation of that. It's not the number one approach you may want to do, because it is a little bit more looking at the object rather than at the principles behind, but it could be a way. Like, it's not the first time we follow such an approach. Because I think you may get something that is quite nice. I mean, the image on the right is actually quite nice. It has some qualities, and with a bit of more work about densities and transparencies, and you can actually turn it into an architectural object. But it may not be this self-sustained architecture that we are talking about.
like what it is. I mean, I'm not sure I get it. Sorry.
Let's say you can say that this building is a canopy, right? Or it can be a roof. It could be a house, effectively, right?
Like if this is made of agents.
For instance, it could be. I mean, somebody could, if you take that piece on the right and you 3D print, you're gonna get an architectural form in a way, right? It's not designed to be that, but it's using the principles of cloud formations to generate a building. Whatever the building is, doesn't matter. And then, of course, you can tweak the simulation processes to get a different building and generate a family and a series of buildings. But this is kind of using the cloud as an inspiration to generate architecture. It's not really using the water vapor to generate architecture. Is an interpretation of it. It's more graphical rather than material. And I mean, it could happen. It has happened many times. It's not, but if you struggle too much trying to get some architectural element out of it, that could be a process.
We were planning to do this part when it becomes ice.
Well, similar then.
Yeah, I think this process maybe can combine, but it's also logical.
But what do you mean when it turns into ice? Like,
when temperature is that low,
yeah. But in your story where you collect the water and then you direct the water, where the freezing moment happens.
It happens, we say that it happens according to the temperature. So it's not...
No, that I understand. But
control.
Location-wise, or in the sequence of your project, where does it happen? Like, at the moment you create a water-based architecture, let's call it, right? You have these units that they collect vapor and they start elevating, and then you want to direct them to drop into a specific location where they need water, right? From what I understand. And then they do the water whatever they want with it. Now, freezing the water and the fractal formation and all that stuff that you were showing earlier, where are they actually, in this story, where are they located?
Like in the story of releasing water, for example, they're located in the atmosphere, because the temperature in the atmosphere, like you can have a cold temperature, which...
So that is in the release part of the story, where you either release that water in a container and somebody drinks this water or whatever they do with it, or you can create a frozen moment of this release action.
Yeah.
That means it needs to be in a very cold environment, because otherwise it won't be frozen. But then it's temporary. No, actually, in a frozen environment won't be a temporary architecture, because it may stay there, but in a warm environment it won't work. You know what I mean?
Mm.
And also perhaps in a frozen environment, the water will be frozen before you release it. So
yes.
I think there will be a decision to be made for your project, whether it follows one or the other direction. Is it more an infrastructural water collecting mechanism and system, or is it more like let's say interpretation of what you can design by using water characteristics? And perhaps we can incorporate also the water materiality in it, but it will be more an interpretation, or what the water flow could be as a design feature in the project. For instance, do you know this Zaha table, the one with the water flow, right? This is kind of generated by the rules of how water flows, but it's a frozen moment in time. It has nothing to do with water. But if you see it, you say, yes, this is water inspired. Instead of somebody going there and modeling the water flow and the way that water moves, actually they simulated and they generated the geometry. So in your case, could be something similar if it's kind of an architectural, more like an architectural element. But then we're going to lose the other part of the story. I mean, ideally we can combine the two, but it can get tricky. On the other hand, it can stay just an infrastructural project and develop all this system as a mechanism of collecting, transferring, and releasing. But that's kind of a decision we will need to take probably after your jury, from what I see.
Yeah, I think it's good to ideally to say that we have both.
Yeah.
Because...
yeah, I think both you can have easily, because there's no reason not to. But the question is, where do you want to focus more?
I think the beauty of itself is that the whole mobility of water itself, like that we are able
that's
to.
very interesting. That's very interesting, actually. That's why I like the infrastructural part of the story. I'm not against at all. But, you know, you may have different opinion.
No, I think that this is the beauty, the mobility of water. And this is actually the same element that could initiate another type of architecture, like the one that you were saying before. So it's like an element that exists both in infrastructure and also in a sculptural perspective. I don't know.
Yeah. Well, I think the big task is to think how we combine those two and to make it, let's say, seamless in a way. So they don't look like two different approaches, but they kind of made out of the same cloth in a way. I mean, material is common, fine, but getting this kind of natural natural transition from one to the other is actually critical.
So should we invest more time now to see the unit and the agent?
Yeah. Look, I think there's nothing wrong with what you're doing. So yes, let's do that. And you know, you're kind of believing in it. And I don't want to kill the spark as such. I think we can, beyond being inefficient, beyond the slide you were describing, being inefficient, there's nothing else that highlights a problem. Well, it's challenging, but it seems that worth trying it. So you start thinking about the unit and implementing part of this lifting mechanism, whatever it is, if it's helium or if it's hot air, and also integrating it into the architecture of it, right? So you have this kind of hair volume, the hairball. Could it be that, I don't know, helium is within this kind of hair? So somehow kind of integrate it a bit more to the actual architecture of the unit itself. Could it be that helium is those very thin elements?
Does it play a role how it is distributed?
The helium?
Yeah.
I don't think so. Helium is lighter in density than air, right? So it just goes above it, whatever, no matter what. Every molecule will go above the a molecule of air. If you mix it, the molecules of helium will go above. The hot air, I guess, needs to be all contained into one container, so they don't mix. But I don't think they need to. I don't think they make a big. I don't think it makes a difference if it's separated or not. Let's say a lot of helium balloons would work the same way, right?
Yeah, and there's this report by Festo, like they tried in different, like hydrogen, helium, steam, hot air.
Mm-hmm.
They compared the volumes between them, like.
Mm-hmm. Yeah, but that's a different one. Like, so it seems hydrogen is even more efficient.
Yeah, but it's highly inflammable.
It's
And
unstable.
they have banned that.
That's why hydrogen motors, they don't go further, although it's better than gas. It's a very unstable gas.
Yeah.
Yeah, okay, but helium is close enough, to be honest. Okay, then think about it like that. Think about this kind of hairy monster infused with helium that captures water on the surface. Let's try to make it as maximum amount of surface as possible on it, so it can capture even more water, vapor, and let's take it from there. And I think the strategy of navigating, it needs to be more using the airflows. So rather than like a mechanical system that drives it, it's more airflows. It's more like a controlled fall. Yeah.
Yes.
And what about this final aspect? Like, Ola, do you want to solve the
One.
issue?
What is the final aspect?
How it captures.
Yeah. So we were basically looking at how it captures, and like one of the inspirations are the spider web being lightened, and they do capture the water vapor from air. So we did some.
I think they capture
studies.
droplets, though. They don't capture water vapor.
No, they condense on the water on the spider webs.
Really?
Yeah.
My God, you're a specialist, really, on that. Everything I say is bullshit.
No. I mean, we're the water team.
I know. No, I think it's,
our best to find anything at this point.
I mean, I'm actually surprised that you have so many solutions to problems that they look impossible. So I think this is very encouraging, to be honest.
Even the dandelion, they can. We found a report by someone talking about dandelions themselves capturing water,
like
their fibers.
Of fibrous systems to capture water.
Yeah, basically. And like we're doing some studies about, okay, what if we have a lattice net in the middle where it can capture water, and like we looked at different how do you say it, lattice organization of these, like if they're minimal, if they're average, how are agents be, like for example, this is an average organization of the netted part, how wind will, like what will it do with wind, basically? Are they gonna still be open, closed? Then we looked at,
is that something you need to start simulating in a way, like kind of the physics of capturing vapor, and what kind of geometric configuration is actually more efficient? Like why a microfiber cloth captures it and something else doesn't, or why would this, let's say, dense mass in the middle will be more efficient? I think it's, doing a simulation in a more macro level rather than in a massive in the big numbers. Maybe it's something you need to explore.
like a close up of this.
Yeah, exactly.
Like a close up, like this one, a simulation of.
I mean, it could be an abstract thing, right? But the image here of the spider web, It's actually an interesting one. So is the configuration of the spider web in the top or in the middle or something else that is more efficient? And what is the geometrical configuration of the fabric they use for this water tower?
Mm.
Is it kind of 90-degree woven one? Is it multiple layers?
Okay.
I think it could be beneficial to just enrich the fact that you want to create more patterning in your unit. Because effectively you need to design it, right? This is kind of an initial design, but if you have to put more detail on it, what is the elements? What are key functional elements into it? Like, how does it operate the best?
Mm-hmm.
Running out of ideas.
We will try to focus on the detail of
Yeah.
that.
Yeah. And do an attempt to fabricate one of those. Like, try to think, how would you do it?
Mm.
Like fabricating one of those without making them float?
With making them float. I mean, why are you asking something you know the answer?
I mean, there are reports.
No, but look, you don't need to think about it 1-to-1 scale, right? You may think it 5-to-1.
Okay.
You may make it bigger than it is in reality. Like that's also very common in prototyping, because you don't have the capacity to do something very small. You may do it 3 times bigger. It doesn't matter.
Okay. Yeah.
But think about the need to fly.
Yeah.
So do we consider how they come closer to
One another.
each other and whether they can connect somehow?
Well,
maybe it's when they connect to each other, they start navigating.
Let's put it that way. I think, what's the reason to connect?
Just to fly more organized, in a more organized.
Okay. We
need attraction, basically. So I don't know if how we can have attraction between them.
Let's start from the first point, how to connect them. I think by nature and the nature of the design itself, when those spikes come together, they will start getting some friction in between, right? So they will attach, not very securely necessarily, but they will attach. And you may detail each of these spikes in a way that actually interlock and they stay there.
Yeah, this was the idea initially, actually, because like a spicule, the same way that a sponge.
Yeah, exactly. So you can think of strategies like that. Now, I'm not sure that once they connect, they will actually navigate easier, or they actually can navigate in a way that we can control, because you can imagine that they will become a mass that is impossible to guide. But that's another story, I think. I think coming all together probably is a good thing to create this kind of cloud formation. And it's a good story overall. Now, if they navigate better, I cannot tell you that. They may fly better because they have more surface for the wind to lift them. But I don't know if they will navigate better. I don't see actually why they will navigate better.
Maybe if they get some formation that helps drag, it helps.
Yeah. But then you need to be able to move, let's say, amend their geometry to make kind of a flight, right? But if you have a kind of a mass of objects, it's impossible to control their movement. So I think it's going two ways on that. I think there may be something to do with when they come together. I think we need to get a bit away from directing them into one specific location and navigate them as such. But what we could think of is whether they fly or they go to the ground. And what is the mechanism between the two? There is a chance when those elements come together, they actually stay in the air because they're almost operating like a wing, like an airplane wing. And then when they dissolve, they actually drop. There is a chance like this, that as a total, they can fly better.
The upward lift of plane, yeah.
For instance. Or they may be the opposite. They may fly alone and they come together and they fall. Could be both strategies. I don't know what would work, but I think like key decisions like coming together or leaving needs to be associated with some others, like dropping and lifting, to just make the system richer. Otherwise, you just make too many different systems doing a different thing, and it's getting extremely complicated. Nature generally is very simple. So once you get inspiration from it, it's good that you keep just the minimal amount of things you need. Like the cloud formation is unbelievable, right? The vapor is lighter, goes up, connects all together, becomes water, and then, oops, falls. That's it. And by the way, there will be a wind that drops the clouds, takes it somewhere else, and here you are.
Yeah.
Mm-hmm.
Okay.
Mm.
So what do you think? What our next step should be? Like, what should we really focus on to make the final review for the space?
I think starting from trying to prototype one of those units, like even if we are gonna ditch it in the next term, but try to do it. Try to make something that can fly, that has enough surface to capture substantial amount of vapor. It's one thing. Second thing is to study the capturing capacities of each of those elements, like what we discussed about different configurations of whether it's a spike, where is a mesh, whether is a whatever other kind of pattern you can have to capture more vapor than it can actually do now. And well, that's in terms of prototyping. I don't think you can do much more than that. It's already substantial amount. Now, if you want to think about computer vision in terms of, let's say, prototype way of thinking, where you kind of have a recognition of patterns, like what you did in this video you had with a color, the white red colored background with the humidity, and there was this cloud that was following. You can perhaps do something similar of some kind of computer vision of reading, let's say, patterns like that, or reading humidity in the air. But I don't think that it's gonna, I don't think it's for that stage. I think trying to build one of those mock-ups, well, prototypes, would be important. Try to make it fly, try to make it capture some of the vapor.
You like dissect this prototype, like it, not one prototype, one does retaining and the other float, and then
I think you can do, yeah, of course. And you need to present it like that. That's what, because it's not about final work, this presentation is about proof of concept that things can happen. But even trying to make this water tower collect water, like build it yourself, it will be a huge learning curve for you, because you see in a video and you say, yeah, it works fine. I bet if you try to do it, you won't make it. Not because you are not capable of, it's because there are a lot of stuff you don't know about it. Even in terms of the fabric, what is it, how does it work? Does it need special environmental conditions? Does it need to be one or the other? So you'll be surprised that it's not going to work that easily. You may need to find some others. I mean, condensation, it's a much easier way to capture humidity, right? Getting a cold object into a warm area is actually very easy and very noticeable. Could it be that your unit actually does that? Goes up in the sky, gets cold, drops, and collects water, so it could be more efficient. So you may even do experiments like that, because it's all about showcasing a kind of a research, right? You can say, okay, I freeze a spoon in -20, it collects this water in 5 seconds. I freeze it in -10, it collects that in that amount of time. So, I mean, there may be some very obvious experiments that they show the obvious, that the colder it is, the more water is going to collect. But then if you start doing that with fabric, if you start doing it with other objects, then it shows that there's a number of things you thought about and you're trying to work around them and incorporate into your project. But trying to showcase that you try to capture from water from the atmosphere is actually something you need to. And to answer your question, it doesn't need to be one prototype. It can be many different ones. I think you're a little bit more worried than you need to, if I'm honest. And I think I was a little bit, I approached your project a bit with this belief a bit, because that's why I'm here, to just challenge it.
No, yeah, definitely.
If I think if you structure it correctly and you filter it better and try to make a point that is not completely out of this planet, you have higher chances to get it in a good state for now, and then we are gonna need to see how we adapt it. But you have some very cool stuff, and you have some nice simulations. Just you need to put it together nicely, and sell a story. It's all about the pitch. Sell the story. Put some physical experiments in between. Some physical prototypes, and this could be a conclusion of the first part of it. But you need to approach it for what it is. It cannot do hundreds of things. It needs to do some things good, so people can get it. At the moment, it's a little bit, let's do everything.
Yes, we are searching. That's why we are trying to push different directions. Yeah.
You know what? I think if you have done a lot of research, you are very technically advanced. Now I think you need to create some stuff and get the architect's hat on and try to do some more artistic / creative stuff, even if they're not necessarily following the science 100%.
In terms of unit or in terms of
In terms of the unit, in terms of the experiments you do, we're not scientists and we are not going to resolve that problem. Maybe it's not resolvable. What you want to do is study alternatives and through the research, guide yourselves to a project that actually is doable. So I think being technical is good, but there's a moment where you need to do a step backwards and say, okay, now I know that what I know, I can search 100 more hours. I'm not going to find something that is going to resolve all my problems. Let's try to generate something, engineer something that may address some of them. May not all of them, but may address some of them.
Like we can focus on the capture and retain part for this presentation.
Yeah, totally. Deliver and release, to be honest, I don't see the benefit for now.
I think that the beauty is that we have the 4 states, to be honest.
I'm not saying you make them disappear, but you need to focus.
But
No,
deliver the cloud, while capture retain is only the agent. But we want deliver, which is the cloud effect, and release, which for me I think is where we could be also more creative and more expressive somehow.
I was talking to the level of detail for now. Like, I don't think we're gonna reach. Like, we have to prove something, and I guess.
I think. Look, definitely you need to keep the overview of the project there, and you need to explain the project as such. Otherwise, it's gonna be a nightmare. So definitely don't stop in 1 to 2. Now, whatever you think you can develop more is better. But in terms of prototype, I don't think you'll be able to go beyond capture and retain.
Yes.
Now, the deliver part could be also part of that, because what we said about this flying thingy, it could be part of the deliver. So there may be a chance there is a bit of a more blurry. Then this prototype covers more than 1 and 2. It could go to 3. But in the release, I think it's just too far for now. You may show some stuff, but I think it's just. I understand what you say. It can be more artistic, but I would focus a bit more in the first 3. Personally, yeah. I mean, at least for a week or 2. I mean, I know you don't have too much time, but you have still 20 days, no, or something a bit less than that.
Yep. So, like this kind of map with the humidity data, is it useful to create like this kind of map? Because this could be further developed. Like it could look like a way of deliver. Is that convincing?
I think this is quite good. I thought it's one of the good ones, those maps.
Okay.
But I don't think you need too much more to explain deliver.
Okay.
But it could be also optimization of how you capture more humidity, because it could be the other way around. You go to capture in the areas that is much more humid, right? You don't want to go deliver where it's humid, because that's where it's going to rain anyways.
Yes, of course. Like
you want to do the reverse.
Yes, it's reverse.
But I think that's kind of interesting. I mean, I wouldn't take it away. Definitely, you keep it there.
Okay. Okay.
Okay.
And this one?
You are one of those persons, you don't want to throw away anything, huh?
Yeah, this one just first tryouts for the prototype sketch.
I was one time in a jury, and you know, on some other people's projects, and there was one guy there and said something amazing to the student. I always remember it. It's not the work that you present to us, it's the work you don't that matters. And the work you put in trust that makes your project special. Because sometimes, you know, we are always like, okay, I did that and this and that, but it's also what you did and you don't use because you did something that is better than that. That is important. So don't be afraid of putting something aside.
Okay.
Okay.
Yeah.
I think the right image though is good, but you need to find the time to show it. I don't know when that is.
I think it's actually can put in the process of our research. It's not conflicting. Like, yeah, we can manage.
Okay.
Thank you, Apo.
Thank you.
Well, I thank you as well. I hope I didn't confuse you too much.
No.
No.
And let's have another chat.
You're grounding us, which is something.
I'm doing what?
You're like pulling us back into reality a bit.
Yeah. I'm trying, but it's not always good. So don't listen to everything I'm saying. But somehow you need to deliver a project, so.
Yeah.
Okay. Well,
we're telling a story anyways.
Exactly. Tell a story, but tell a good story. Tell a good story. That's all you need.
Yeah.
I'm not saying it needs to be super realistic, but don't go nuts, because then nobody takes you seriously.
Yeah.
Okay. Well, speak soon.
Mm-hmm.
Okay. And let me know if you want to chat. I know you always say yes, 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 but nobody sends me anything. Nobody has sent me a single email.
Actually, you appeared right on time right now. I was thinking to send you like this week. So
okay, that's good.
I think that it was right on time.
All right. No, I'm just kidding, but really don't be shy. Just go for it.
Okay.
I'm getting 1 million annoying emails per day. 1 million one is not a problem.
Oh. I can't accept that I am an annoying email.
No, not in the way. Not in that way. I'm just saying.
Yeah, exactly.
But yeah. Okay, let's speak soon.
Okay, thank you.
Are you all in London?
Not me.
Tyler, you naughty. You naughty
I will be
guy.
there soon. I will be there soon.
Tell him to come.
When are you gonna be done with this virus? Because we cannot meet otherwise.
We got the virus and we're fine.
I know, but you need to go through it. Otherwise, we cannot meet.
Tomorrow we finish.
I finished today,
really?
but I didn't go out.
Really?
Yeah, it's 2 weeks now.
Interesting. Okay, we can catch up next week then. Physically.
Yeah.
Actually, we can go for a beer.
That would be great. Yeah.
That's so great. I will be jealous.
Tyler, now he will get a ticket.
You know, now London is like normal. There's nothing weird about it.
Okay, that's nice.
I mean, the only weird part is that you go to the pub, you wear the mask to get in, and then that's it. Doesn't make any sense.
Okay.
All right.
Yes. Okay.
Okay, let's
that's
talk
nice.
next week.
Yeah.
Okay.
Okay, see you soon.
Okay.
Bye.
Okay. Thanks. Bye.
Bye.
Bye bye.
Bye.
Bye.